So I'm Jonathan Hu. Christian Glusa is up there. He's going to be circulating during the hands-on. We're part of the Algebraic Multigrid development team at Sandia National Labs. So we'll be talking about that, plus some Krylov solvers to begin with. Let's see. So because we didn't know the background of people here, we sort of decided to start at the basics. And so for a lot of you, this may be a review, but we're hoping it's going to be beneficial for some folks. And so really, we're interested in solving very large sparse linear systems, of the form AX equals B. And we're assuming here that A has not many non-zeros per row. And I'm not really going to define what not a lot of non-zeros means. But the canonical problem that we're going to be looking at is Poisson. So like a 2D Poisson problem here that we've seen previously, formed from doing central finite differences on a uniform mesh. And I guess for Anne, this is like uniform. And so in this case, we get 5 entries per row. Now, you could store it as a dense matrix where you store the non-zeros. But for this crowd, obviously, you want to be smarter. You want to store it in a compressed, in a sparse format. There are different formats that you can choose. A very common one is CSR or CRS. It depends on, I think, where you did your graduate work, how you abbreviate that. You have essentially 3 arrays. You have a row pointer. You have an array which points into 2 other arrays, indices and values. There must be a pointer here. Oh, I don't think I need it now, but it would be good if you could get it out. So you essentially have these 3 arrays for storing the sparse matrices, and so this is what we're going to operate on. Okay, so solvers that we can use when we're trying to solve this linear system AX equals B. So the very first option is a direct solve, so something like Gaussian elimination. But that factorization, that scales like n cubed, where n is the size of the problem. This also has, so if you can do a direct factorization and you don't care about time, it's a fine way to go, but it's not scalable. The problem is that the factors are much denser than A typically. And so there's a cost in memory. Doing a parallel implementation, there are good parallel direct solves, but they're not easy. SuperLU is one. There's mumps, and SuperLU dist, mumps, and I believe there are probably others. The advantage is you don't need to know a lot about the structure of A necessarily. But since we know that A has order n non-zeros, and so an optimal complexity for a solve would be something that's O of n. So the second option, if you're not going to do a direct solve, is an iterative method. And the nice thing is that we can exploit an operation that has already been referred to earlier today, and that's the sparse matrix vector multiply. Some people call it a SPIMV. I'll probably refer to it just as a MATVEC. The great thing is this is easy to parallelize. It can have a small memory footprint, depending on the solver that you end up implementing. But there are more restrictions on the structure of A that may be required. So the first set of iterative methods that I'm going to talk about you've already seen them today. Krylov methods. There was a really nice talk that Jim Demmel gave this morning. So based on sparse MATVECs, we can do computations of this form here, where we do updates based on a residual, and we can recombine these using this. If I can find the button here. We can recombine these to come up with approximate solutions. And typically, we're doing inner products using powers based on this space, which is powers of A. This is the Krylov space. And so we're choosing solutions from here that satisfy some sort of optimality condition. Now, keeping the entire Krylov space can be expensive because you're essentially storing dense vectors. And so that's could be one downside. Computing inner products, that usually requires an all reduce if you're running in parallel. Well, it does require an all reduce. And as you scale up the problem in terms of the number of MPI ranks, this can be costly. There are ways to sort of take care of that, but in general, that can be costly. So the two Krylov methods that I'll mention are first conjugate gradients, CG. This is nice if you've got a symmetric positive matrix A, then it's applicable. It has a short recurrence, so you don't need to keep the entire Krylov space. The other main workhorse that we usually use is called generalized minimum residual, GMRes. This works for non-symmetric systems. One feature of GMRes is that you need to keep the entire Krylov space. You need to keep this entire space here. Now you can do something called restarting, which means after k iterations, you throw away the space and you restart. But that comes at a price in terms of convergence. So we know that for CG, we can bound the error of the kth approximate solution by this formula here, where kappa is the condition number of A, right? Kappa is given here. Okay, and this is pretty typical for Krylov methods. And the condition number can be viewed as a way of measuring how hard it is to solve the system. So the idea with preconditioning is that you want to reduce the condition number of the system. So instead of solving the original sparse linear system AX equals B, you want to come up with some matrix P and solve either this transform system or this system here. Left preconditioning, P is on the left, or right preconditioning, where P is on the right. Okay, and the idea here is that the condition number of for a good preconditioner, the condition number of the preconditioned system should be much less than the condition number of the original system. But this sort of has, there's sort of two ideas which are in tension here, is that you don't want your the ideal preconditioner would be A inverse, but that's if you could even compute that, that's very expensive. And well, he's got it here, and but you want it to be cheap. Right? So A inverse would be an excellent preconditioner, but you also want the application of that preconditioner to be relatively inexpensive. So there are some simple preconditioning ideas. You can apply Jacobi, where you're only using the diagonal of the system. You can use Gauss-Seidel, where you're using the lower or the upper triangular part of the sparse linear system. Another one which we actually use quite a bit in practice is a polynomial preconditioner, where the polynomial is based on powers of A. And you have to take some care in choosing which polynomial you use. You can move up, and then you can use incomplete factorizations, such as ILU, incomplete Cholesky, or some variant of ILU. So those are some simple preconditioners that we can apply. So all of these and more are actually available, and Trilinos has been mentioned previously. These are all the preconditioners I just mentioned are available in Trilinos. There's also the Krylov methods I mentioned and more. So Trilinos, the goal here is we want to tackle very large-scale, complex multi-physics problems. Trilinos provides, besides solvers, it provides just a whole sort of passel of things, discretization methods, meshing tools, AD tools, linear solves, nonlinear solves, preconditioners, eigensolvers, optimization, UQ libraries, and I'm sure there are more on this list that I have missed. And it's mostly C++. There is some C in there, and there might be a smidgen of Fortran, but I don't think so anymore. Hopefully it got cut out, not to offend anybody. But a big selling point for Trilinos is that it's MPI based, but it also allows for this plus X idea. So where we can run with various backends, OpenMP, CUDA, pthreads, using this thing called Cocos, which I think you saw last week. Christian Trott talked about it. It's open source. It's on GitHub. And then two of the workhorses for the linear solves is Belos is the first one. This provides standard Krylov methods. So CG, GMRes, and then TFQMR by CGStab, et cetera. There are more advanced methods, so block methods. Jim Demmel talked about tall, skinny QR. Mark Holman, who is one of the developers of that, is a Belos developer at Sandia. There are recycling techniques in there. There's also quite a bit of active research in communication avoiding methods and pipelining and S-step methods. So IFPAC2 provides some of the simple preconditioners that I just mentioned, so the incomplete factorizations, and then the various relaxation preconditioners like Jacobi, Gauss-Seidel, SOR type methods, and then polynomial methods like Chebyshev. And then it also provides a domain decomposition capability as well that I won't talk about in any detail. So so this is actually, we're going to now segue and we're going to go to the hands-on. And the hands-on portion here is just going to look at the the non-multigrid part of Trilinos. So let me flip over here. So let's see. I think if you copied, if you r-synced anytime today, you should be good. But if you have an old copy from like yesterday, you should definitely r-sync over again because we made some changes this morning. Let's see. All right. All right, and I think that Mark has opened up. There are going to be various points where we ask questions. We decided it was maybe more useful to have the answers to the questions display there rather than you do form submissions. All right, so here what we're going to do is, if you'll just change directories into the Krylov_AMG subdirectory, then you should see two executables. One of them, the _GPU, you can ignore. We're not going to use that right now, but I think in the evening activities, you could try that out. We're going to be using this executable here, this one, mulu_stratamikos.exe, and then we're going to be using an XML input deck called stratamikos parameterlist.xml. We do have a capability of using YAML, but I'm a little more comfortable with XML, so that's just what we're going to go with. All right, so we're just going to solve the Poisson's equation here. All right, and we're going to be working on a regular square mesh. And let's see here. The very first thing to note is if you need help, you can just do mulu stratamikos --help, and you'll see quite a bit of output options, but these are kind of the main ones here. Just sort of specifying the problem size, the mesh size, the matrix type, the input deck. There's a capability if you wanted to read in your own data, you could do that as well. So that should be, there's no code compilation or code changes here. We're going to be doing everything from the input deck. And so let's see. Okay, so the very first thing we're going to do is we're just going to run it as is. right? And what you should see is, you should see an output very similar to what we've got right here. Let me see it, maybe I'll make that a little bit smaller. That's still readable. Yep. Okay, I'll do that here just to keep myself honest. Oh, you know what? I didn't get a, well, I'm running on the head node, so hopefully that's okay. Hopefully nobody will bark at me. And so what you can see here is you see a little bit of preliminary information telling you problem sizes. We're running a 2D Laplace. It's a 100 by 100 mesh. And then you see a header for Balos. It tells you that you're using something called pseudo-block GMRes. The pseudo-block means that you could solve with multiple right-hand sides, but it would solve each right-hand side in turn. It wouldn't actually be doing a true single solve. And so then we can see that we solve for 100 iterations, and we see a failure. And so I guess the question is, why do we see a failure?
Like maximum iterations without achieving the convergence.
Yeah, we've hit 100 iterations, and we have not achieved the specified tolerance here, which is we asked for 8 orders of reduction in the residual. That's right. Okay, so it's a little small. It's going the wrong way. There we go. Okay. All right, so let's go ahead then, and you'll see whenever we ask for you to change something, you'll see that little orange play button. So let's go ahead and change the input deck. And let's change it to use conjugate gradients instead. All right. So. All right. Okay, and the question is, do we see sort of we still see a failure here. And the question is that to be expected? Maybe, no, yes. Right, it's still unpreconditioned, right? So yeah, the answer is yeah. We expect, just because we're switching to CG, yeah. We shouldn't expect any necessarily convergence because we still are not doing any sort of preconditioning here. All right, so in fact, we pop this open. Oh, thank you. Yeah, let me try that again. Right, okay. Okay, so then the next question is well, why should we use CG instead of GMRes? So the problem is symmetric. So let me phrase it another way. Is it advantageous to use CG in this case?
Yeah.
Why is that?
Symmetric metrics.
What's that?
It's cheaper than GMRes for symmetric.
Sorry?
It's cheaper than GMRes for symmetric system.
Cheaper than GMRes for symmetric?
Yep. And it's cheaper because we don't have to keep we don't have a long recurrence, right? So we don't have to keep the Krylov space. That's right. Okay, so let's go ahead and let's go ahead and verify that. You can actually copy this string here, and you can actually look at the memory requirements of CG versus GMRes. So since we've got CG, let's see. I'm going to run this time command here, and I'm grepping out the memory requirements in kilobytes, and I can see it's about 230K. And then if I switch back to GMRes, I rerun. Boy, running on the head node is painful. It's about twice, right? The memory requirements are about twice here. Right, so we can see, this is empirical evidence that, yeah, okay, it's, in this case, there is a memory advantage of using CG over GMRes. In fact, let me see. I'm just curious how quickly it will, if I'll get this.
You trying to get an allocation?
We'll see.
It only takes 15, 20 seconds.
Okay, all right. So let's go ahead then, and let's move on, and we're going to stick with CG for the moment, or for the remainder here. And let's go ahead then, and we're going to do some modifications now and try simple preconditioners. So things other than sort of that algebraic multigrid would use, but a little bit simpler. So if we look at the input deck, for example, on line 74, perfect, I got one. Or roughly not 74, we can see that we have a preconditioner settings for the IFPAC2 library inside of Trilinos. So this is what provides like SOR type methods, polynomial preconditioning. All right, so let's go ahead and we're going to change the preconditioner type, which was none, and we're going to change it to use IFPAC2. So that's on line 59. Okay, right here, and we're going to switch to IFPAC2. Yep. Okay, and we'll rerun. Yep. Oh, okay. Maybe that's easier to see. All right, yeah. Let's see if that's better. All right. Okay. Okay, and so when we run, let's see, oops. We did a run here. And the question is, did the preconditioning help in this case? No. So why did it not help? What's that? Right, so it's not a symmetric preconditioner, right? So what we have, so we're running CG, and so CG requires symmetric preconditioning. And if you look here, we're running Gauss-Seidel, not symmetric Gauss-Seidel. And so what we're going to do next is we're just going to go ahead and... let me double check. Let me just double check here. Oh, yep. Let's look. Oh, I still have it on GMRes. You're right. Thank you, Mark. I was hoping Christian would catch that for me. Okay, let's try that again. Yeah, it's actually, this is even worse, right? So we're running CG, we're running it with Gauss-Seidel. It's a non-symmetric preconditioner. And this convergence is actually even worse than what we saw previously. So now let's go ahead and switch it to symmetric Gauss-Seidel in the IFPAC2 block. IFPAC2. Okay, down here, it's about line 81 for me. Depends on how you did your commenting and uncommenting. Okay, rerun. Let's see here. Okay. And I see that, in fact, I've got convergence, right? Okay. And so let's go ahead and, so we can do other things if we're staying with a simple iterative preconditioning scheme like symmetric Gauss-Seidel, we can increase the number of sweeps. So let's go ahead and do that. Okay. And we see that we have evidence, increase the number of sweeps. We're increasing the effectiveness of the preconditioner at a cost because we're having to do essentially more matrix vector products, right? So there's a cost here. Okay, and now the next question is, we've so far been running with a fixed problem size. So now let's go ahead and run a sequence of problems here where we increase the mesh. We'll go from like a 50 squared up to 200 squared, and let's look at the behavior of the solver. Okay, so now we're going to do an x equals 50 and y equals 50, right? Yep. Okay. So we see we've got 29 iterations. I think we were running by default, we were running 100 squared. We see it grows to about 53 iterations, and then we go to the largest problem, the 200 by 200. And we see that we're at 94 iterations, right? So the question is, is this what we would consider scalable? No. I see no over here, but then did I hear a yes? Yes, scalable. So okay. So the answer is no, it's not scalable. That we're increasing the problem size, and we see that the iteration counts are increasing, right? And so ideally in the ideal case, as we grow the physical problem size, we would like to keep the number of iterations more or less constant, right? So that's what I'm looking for in terms of scalability. Okay, and so we can click on that, and that's what we'll see here, right? Right, so in fact, we can see here, let's see, right. We can see that the number of iterations, it scales with the square root of the condition number of the preconditioned system. Unfortunately, we don't print out the condition number. Christian tells me that we can't actually do that. It is possible, but okay. Oh, it requires code changes. Okay, so we're not going to do that in here. All right. So we cannot do it with the current driver. Yeah, that's an evening hands-on. You can modify the appropriate code. No, just kidding. All right. So let's see. So based on the iterations, how does the condition number scale with respect to the number of unknowns? Proportional, linear, anything else? It doesn't scale with respect to the number of unknowns. Right. Right. So we can see that the iterations is growing up by a factor of 2, right? And the size of the problem is growing by a factor of 4, right? So it's proportional to the number of unknowns. Okay, so I think now we want to jump back over before we go on to set 3. And we're going to look at multigrid methods. Let me go back here. There we go. All right. Well, we'll let this play. Okay, so this is kind of the motivation for multigrid methods. So this is a really nice sort of an illustration of the convergence of just Jacobi. So we're not doing a Krylov method. We're not doing multigrid or anything. We're just running sort of a diagonal preconditioning or a Jacobi. And what we can see is that when we start with this initial error here, let me bring it back. Pause here. So this is our initial, this is error here, Christian. Is that right? We verified this is the error. And as we run Jacobi, what do we see about this error plot? How would we characterize that?
High frequency errors just tweakage drops.
Yeah, so you can see that we've got a lot of sort of very high frequency, highly oscillatory error, and it's quickly getting damped out, and what's left behind is essentially relatively smooth error that's has a fairly broad support. And that's a characteristic of Jacobi and many other smoothers. The smoothers are very effective at quickly damping out this high frequency error, but the low frequency error is very slow to be damped out. Okay, so that's one sort of aspect of smoothers. Okay. And then we can look at sort of how Jacobi transmits information. So again, we've got iteration counts on the right. And over here, I believe this is the, Christian, this is the solution? Christian? This is the solution here?
That's the solution.
That's the solution, right? And what we can see that as Jacobi progresses, we've got a point source in the middle, and that we're sort of slowly resolving things here. And the point that we're trying to illustrate here is that Jacobi can only sort of transmit information locally to neighbors. So as you take an iteration of Jacobi, essentially you're transmitting information to nearest neighbors. And so by itself, Jacobi and it's that family of smoothers, they can only transmit information locally. And so as you grow the problem, well, that transmission is going to take longer and longer, essentially. So the idea of multigrid methods is that you want to introduce something that will give you more global communication. Okay, and so we'll motivate things with geometric multigrid. And then we'll talk about relations to algebraic multigrid. So in geometric multigrid, you essentially you're starting with some fine mesh up here. This would be where the application has defined its problem. And then you form a sequence of coarser meshes. And then you do a rediscretization of the problem on each mesh, each subsequent mesh. Okay, and you can, from what we just saw, we can see that if you run a smoother here, it's going to tend to damp out high frequency error very quickly, and it's going to be left with low frequency, what appears to be low frequency here. Well, if we can transfer that in the appropriate way, then via aliasing, that what looked low frequency here will appear high frequency here. We can run smoothers. That smoother will damp out the high frequency error, leave low frequency. We transfer that error down to this third mesh here, where what looked low frequency here will appear high frequency here, and then we can run the smoother again. So you can just sort of recurse. And typically on the coarsest level, you would do a direct solve. Right. So this is kind of what I said in words. We have smoothers. There's usually two that we refer to. We refer to pre-smoothing. So this is before you do any transfer of information to the coarse level. So and then we have what's called a post-smoother, which would be the smoother that you run after you've transferred information back up to a grid, to a level. And the way that you move information back and forth, these are called the restriction and the prolongation operators. Restriction is when we're moving information down. Prolongation, these P's are when we are moving information back up. This sort of schedule of visiting the grids is what's referred to as a V cycle because it obviously has a V shape. If you were to add, let's see. So Okay, got that. So here's the recursive algorithm. If you were to add an additional call here, then you would get something called a W cycle, and that can be sort of generalized. You can add additional calls. In practice, people generally use V cycles. You occasionally will use a W cycle, but the W cycle will really emphasize spending more time on course levels. And in parallel, that's often not what you want to do. That does come with a cost. Okay, but anyway, the main idea to take away here is that you have different multi-grid levels. This is called the hierarchy. And on different levels of the hierarchy, you want to attack different components of the error. And the optimal behavior, which we're aiming for, is to have convergence in a fixed number of iterations that does not grow with the size of the problem. Okay, so that's geometric multigrid. Geometric multigrid is great if you can do it. It does require it requires having a sequence of meshes. So that typically that's on the application to create those meshes. Then they have to do a rediscretization. And it's fairly intrusive in terms of getting the grid transfers between levels. That usually requires some information about the discretization itself. So an alternative to that is algebraic multigrid, where if you don't have geometric information, you don't want to supply the grids, maybe you have an unstructured mesh, and so it's difficult to come up with transfers or to come up with coarse grids, then you can, in AMG, that will be done automatically for you. The user will supply only their fine grid matrix A, and then the algebraic multigrid library will develop those coarse levels in a semi-automatic fashion. Okay? It is an automatic fashion, but maybe we need a little more information than just the matrix A. But classically, you would just provide A. There are kind of two main classes of algebraic multigrid. There's what I will refer to as classical algebraic multigrid. This is what's done in Hyper, where you start with the fine grid unknowns and you select a subset of those to form your next course level, and then you repeat. The other main type of multigrid is aggregation-based, where you group a fine grid. You group a set of fine grid unknowns together into what's called an aggregate, and that forms a single unknown on the course level. So sort of a key principle for, it doesn't matter which multigrid you're algebraic multigrid you're talking about, is that you want to make sure that you respect what we refer to as the near null space of the problem. And it's near null space, so it's not a true null space because of boundary conditions. But the main point is that near null space is associated with error that's going to be hard to converge. It's going to be very slow to converge, and so that's the thing that we want to preserve on course levels. So here we have sort of a 2D illustration of aggregation, and here is a 3D illustration of aggregation. So there's a number of very good software libraries that provide AMG capabilities. Hyper has already been mentioned from Lawrence Livermore National Lab. Actually, it's actually Boomer AMG is the multigrid package inside of Hyper. Hyper is more than that. I think Ulrika is going to be joining us tonight online if you want to talk to her. PETSI has a smooth aggregation-based multigrid that was developed by Mark Adams and the rest of the PETSI team. I think Barry Smith is up in the back row, and he'll be around this evening if you want to talk to him. And then in Trilinos, we actually have two multigrid packages. One is called ML, and I told my colleague who developed ML that he should have copyrighted that, but it's too late now. It's a C library. It's MPI only, so it is limited to, and it is only limited to 32-bit integers. So lots of users, but it's just sort of under maintenance right now. The main library that we work on is something called Mulu. It's templated, it's C++. We can go past 2 billion unknowns. And we have the capability of running on, we can do MPI plus X. We can also run, so we can run on multi-core CPUs, GPUs, and other types of other accelerators. So let's see, just a little bit more about Mulu. These are some of the applications that it's used in. It's aggregation-based. We have a colleague who's been actively working on putting in structured coarsening. So if you have a structured mesh or a logically structured mesh, there are some nascent capabilities there. And this has advantages if you want to run on advanced architectures. There's a whole lot of smoothers that you can use that we've already mentioned. A big key, which we're not going to do this afternoon, but can be done in the evening session, is load balancing. That really comes into play if you're running very large-scale problems. And there's lots of interesting ongoing research for next-generation architectures, multiphysics, coupling structured and unstructured problems, and then algorithm selection via machine learning, so AMG via ML. All right, so let's go to the next hands-on, which is the algebraic multigrid part. Let's see. So this will be set 3. All right. So now we're going to go and change the preconditioner that we had here, which was ifpac2, and it's around line, in the hands-on it'll say 59, so it'll be kind of there depending on how you commented or uncommented. Okay. Okay, and we just want to go ahead and run the same set of problems that we ran previously. Okay. All right, and let's see here. So what do we see in terms of iterations? So we see relatively flat iteration counts, somewhere around 10 or 11, okay, which is kind of, that's what we wanted to see. So is this something that we would consider scalable? Sure. Right? We've got a fixed number of iterations as the problem size grows. Okay, so let's go ahead and look at the output. So we're running the 200 by 200. And if you're getting, so there, yeah, actually, do I have it here? I do. Okay, and I'm just going to look at the output here, starting at the line labeled multigrid summary. All right, and actually let me go ahead and pull this over to the same screen. All right. Come on here. There we go. All right, so there's some information that's kind of useful if you're looking at a multigrid method. Maybe the first part is the first key bit of information is the number of levels that the multigrid method created, in this case 3. Then you'll see the next 2 lines, operator complexity and smoother complexity. And let's see, let's go ahead and actually, well, we'll come back to those in just a minute. The cycle type, in this case, it's a V cycle. You could have selected W. Then there's a little more, after that, we're going to see more information about the matrices on each level, number of rows, number of non-zeros, the coarsening rate from the last level, the number of processors involved, in this case, 1. And then after that, we can see information about the smoothers on each level. And in this case, we see that we're doing just Jacobi with a damping factor, and then we're doing a direct solve on the coarsest level. So the two things that I want to go back to are the operator complexity and what's called the smoother complexity. So the operator complexity is given by this formula here. The number of non-zeros, a summation of the number of non-zeros in all the levels over the number of non-zeros just in the fine level matrix. So the question is, why is this helpful? How would this help us assess potential performance? This complexity. Why would we care about this?
Memory storage.
What's that?
Memory storage.
Potentially memory storage. Maybe let me ask a related question. What would be an optimal complexity? Bigger or smaller? We see the complexity here is 1.33. So do we want that complexity to grow? And if so, to what? Or do we want it to go down, and if so, to what? Well, we know that the number of non-zeros in the fine level matrix, that's fixed, right? And we're summing up the non-zeros in all the levels, including the fine level. So what would happen if we had no coarse level? What would that ratio be? It would be 1, right? And as we add levels, as we add coarse level matrices, that number is going to grow bigger than 1. And so this complexity kind of gives us a sense of relative, if we were going to do a MATVEC on the fine level, what's the relative cost of doing MATVECs on all the levels? Roughly, you can think of it that way. So if we've got something closer to 1, that's great. As it grows, if the complexity were 6, well, then, that would be problematic. Because that's telling us that, it's about 6 times more expensive to do MATVECs on all the levels than just the fine level alone. All right.
How could it be very high? Because if you increase the number of levels, it should be coarser and coarser, and so it should only have
So that's a good question. How could it grow? Well, so if you did perfect coarsening, then you could keep things under control. But because we typically work with unstructured meshes and we don't have these perfectly shaped aggregates, you actually get growth in the number of non-zeros per row. And so you can actually see, I've actually seen complexities very high. So that can happen. This is a good question. All right, so let's, last one is smoother, the next question is smoother complexity. So, the smoother complexity is very similar to the operator complexity, but it's measuring, instead of looking at the number of non-zeros in the matrix, it's looking at how you would, the number of flops that you're going to do in the smoother compared to the fine level. So why is that of interest? So why would the smoother complexity tell you something different than what the operator complexity tells you? So the smoother complexity is telling you that if you've got something simple like, let's say, Jacobi or Gauss-Seidel, then you're passing through the matrix essentially like a MATVEC. So that smoother complexity should be really close to the operator complexity. But let's say you wanted to do something heavier duty in your smoother. let's say you wanted to do multiple sweeps of a smoother, or let's say you wanted to do an incomplete factorization, how would you expect the number of non-zeros in the incomplete factorization to compare to the original matrix? Should be much higher, right? And so you would actually expect that your smoother complexity would actually be higher than what your operator complexity tells you. So the smoother complexity is going to tell you for the particular smoothers you chose, how expensive is it to apply those smoothers versus the fine grid. All right, so let's go ahead and see what happens if we try a few different smoothers. So let's first change, let's run a larger problem here. So it's the same problem that we have. You don't need to make an input deck change. Okay, and let's just run here. Oh, in fact, I ignored my own instructions, or the instructions that were recommended, which is let's do some grepping so we don't have to look at all this output. Rerun it. Okay, and so I'm pulling out here the total solve time and the number of iterations. So I see 12 iterations in about almost 1 second. Okay. So now let's go ahead and I assume everybody here has a compute node. Nobody's running on the head node. So you should have pretty consistent timings. All right, so let's go ahead and change over to Gauss-Seidel versus Jacobi, and let's see what happens. Let's see, where's my input? Okay. Jacobi. Okay, and there are two different ways that you can actually do the symmetric Gauss-Seidel. You can either do symmetric pre, symmetric post, or you can keep it symmetric by doing a forward Gauss-Seidel in the pre-smoother and a backwards Gauss-Seidel in the post-smoother, which will keep the whole multigrid method symmetric. So I'm actually going to choose to do, I'll do the second one, where I do a forward in the pre-smooth and backwards in the post-smooth. Let's go ahead and compare this. Okay, and I can see that in this case, it's a little bit less time, and I've reduced the number of iterations here. Did anybody do the other one, the symmetric pre-smoothing and symmetric post-smoothing? And how did it compare? About the same. Runtime too?
Yeah.
Okay. All right. So let's go ahead and we'll stick with whatever symmetric Gauss-Seidel you have. And let's go ahead and run a sequence of problems where we're just going to keep the same global problem size. We're just going to throw more MPI ranks at it. Okay. So I'm going to do 2, 4, 8, 12. Okay. And so what do we observe when I add more and more ranks? So same global problem size. So I can see, I should tell you these timings here. So this is min, average, max, and ignore this last number in terms of timings. So what observations can we make when we throw more MPI ranks at this? Timing, yeah, times go down. What about number of iterations?
More or less the same. More or less the same.
More or less the same. So there's a little bit of variability here. And, okay, so question is, where does that variability come from? So one thing that maybe you can't know, unless you know something about multigrid methods already, the coarsening could actually change depending on the number of MPI ranks that you have, because coarsening is kind of happens on a per process basis. But there's something funny about Gauss-Seidel, or something interesting, I should say, about Gauss-Seidel, which is when you run it in parallel, it's not a true Gauss-Seidel. It's only doing Gauss-Seidel on a per process basis. It's actually doing Bloch-Jacobi, and the updates between ranks is actually, it only occurs after everybody has swept through their unknowns. So the convergence is going to be not quite the same as a true Gauss-Seidel. So you're going in a different order, that's one thing, and then you're also sort of using somewhat stale off-processor values. So that's going to affect the convergence. So let's see, so the last thing is, here's a good question. Can we adapt Gauss-Seidel to massively parallel architectures? For example, like you might see on a GPU. Why would it be difficult? Gauss-Seidel is essentially a serial algorithm because you're sort of sweeping through, let's say, 1 to n. You need 1 through n minus 1 to be updated before you can update the nth equation. That's right. And so it's possible to eke out some parallelism from there, but it's not easy. You can do things like multicoloring, for example, but there's not a lot of potential there for parallelism. So the last thing I think we want to do, because we're running up against the hour, are we not? Okay. So the last thing I want to do is I want to change the smoother to a polynomial, which is Chebyshev. Okay, and let's see. So you want to go to line 155 here. And as I'm making that change, I'll just say that Chebyshev has some advantages. It's based on a sparse matrix vector product. So that's not going to change as we change the number of MPI ranks. A sparse matrix vector product has, well, it's a well-optimized kernel. A lot of people have worked on it. There's a lot of opportunities for parallelism. Okay, so let's go ahead and rerun these same problems here. Okay, so we can see that the times are dropping, and we can also see that the iterations are constant in this case, right? And that's a reflection of sort of consistency in the smoother, that because it's a matrix vector multiply, we can, we're essentially getting the same answer regardless of the number of MPI ranks that we throw at it. So there's a little bit, there was more which sort of had to do with how do you deal with a common issue, which is when you have a problem where you have material variation, mesh stretching, or something else that causes anisotropy. We were going to look at the aggregation threshold, but that's something that we'd be happy to, you can run in the evening, hands-on. We'd be happy to talk to you about it as well. But I think at this point, I'm going to stop. All right, thank you.